Imagine you want to discover something new. What's the very first step you'd take? Would you just guess? Would you look for clues? Would you try something and see what happens? From the rusting of iron to the development of vaccines, from the bubbling of vinegar and baking soda to the discovery of radioactivity, every scientific discovery, big or small, begins with a question and a deep sense of curiosity. This is where science truly begins. Throughout history, scientists have asked big questions about the world and used careful experiments to find answers that changed everything, from how we understand matter to how we improve medicine and technology. But how do scientists actually figure out the secrets of the universe? How do we go from wondering why something happens to actually knowing how it works? And just as importantly, how do scientists make sure their answers are reliable? History gives us powerful examples of this in action. Antoine Lavoisier, known as the father of modern chemistry, discovered that oxygen is essential for combustion and proved that matter can't just vanish. It only changes form. His work helped transform chemistry into a precise science. John Dalton introduced the atomic theory, showing that everything is made of tiny atoms, each with unique weights and properties, fundamental to everything in chemistry and physics today. Thomson discovered the electron, the tiny negatively charged particle inside atoms, revealing that atoms aren't indivisible, but have complex internal structures. Mendeleev arranged the elements into the first periodic table, organizing them by properties and atomic weight, predicting the existence and characteristics of elements yet to be discovered. Gilbert and Lewis developed the idea of chemical bonds formed by sharing electrons, unlocking how atoms connect to form the molecules that make up everything from water to DNA. Marie Curie discovered radioactive elements like polonium and radium, opening up new frontiers in medicine, energy, and our understanding of atomic science. Together, their discoveries laid the foundation for modern chemistry, helping us understand the building blocks of matter and how they interact to create the world around us. But how did these scientists know their findings were true? Most of them used the scientific method, a systematic process of asking questions, making observations, forming hypotheses, testing them through experiments, and analyzing results to reach reliable conclusions. The scientific method is at the heart of how scientists across disciplines explore, understand, and explain natural phenomena. While its specific application may vary depending on the field and the nature of the inquiry, its core principles remain universal: curiosity, systematic observation, rigorous testing, and openness to revision. The scientific method is a systematic process for generating reliable knowledge about the natural world. It begins with formulating a research question, a guiding inquiry that defines the scope of investigation and establishes a clear direction. Scientists then make careful observations and conduct background research to gather evidence and understand the phenomenon more deeply. Based on these observations, a hypothesis is constructed, a testable explanation that can be evaluated through experimentation. Experiments are designed to be measurable, controlled, and repeatable, producing data that can be analyzed to identify patterns, relationships, and insights. From this analysis, conclusions are drawn about whether the data support or refute the hypothesis. This process involves considering limitations, distinguishing correlation from causation, and evaluating alternative explanations. The scientific method is inherently iterative. Hypotheses may be refined, further experiments conducted, and additional data analyzed in a continual cycle of testing and revision. Once conclusions are reached, results are communicated through publications, conferences, or reports, allowing other scientists to evaluate, replicate, and build upon the work. Independent verification and retesting help ensure that findings are robust, reliable, and broadly applicable. Through this structured yet flexible process, the scientific method turns curiosity into dependable understanding, advancing knowledge step by step while continuously refining prior conclusions. When a hypothesis has been thoroughly tested and shown to explain a wide range of phenomena, it may be developed into a scientific theory. A scientific theory is a well-substantiated, comprehensive, and testable explanation for a broad set of natural phenomena. Theories explain why laws work the way they do. They are not guesses or opinions. They are backed by vast amounts of evidence and remain open to revision in the face of new data. When experimental observations are repeated many times under the same conditions and always produce the same results, scientists may formulate a scientific law. A scientific law is a concise, often mathematical statement that describes a consistently observed pattern in nature. Significant examples of chemical laws include the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. Throughout this process, scientists remain open to revising or rejecting hypotheses if new evidence emerges. This self-correcting nature ensures that science steadily approaches a more accurate understanding of reality. By following the scientific method, observation, hypothesis, experimentation, analysis, and verification, these chemists were able to uncover profound truths about matter that continue to influence technology, health, and our everyday lives. This disciplined approach remains the foundation of scientific progress today. Until next time, stay curious and keep exploring.